You can go in physical time, in the time that is ticking. You can go infinitely many ticks back. The universe still exists.
Welcome, YouTube. So many of you will know I've got a book coming out that I've co-authored with Nihaya Shafshordi on competing models of the Big Bang. And several of these ideas imply that the universe might be eternal into the past. One such proposal is the slow freeze picture of Christoff Wetterich, a professor of physics at Heidelberg University, well known as one of the leading figures in quantum gravity research, specifically in asymptotically safe gravity. And if you want to see more about that theory, click on the link in the description below. But right now, we're going to be talking about this slow freeze alternative to the Big Bang with none other than Christoff Wetterich himself. So welcome, Christoff. How are you doing?
Hello, welcome to Fturue, to see you again.
Yes, good to see you. So why don't we start off, what is the slow freeze picture and how does it differ from the conventional Big Bang?
Well, in the Big Bang picture, the universe at early times was very hot plasma, and it was smaller than today. And then, as time goes on, it cooled and expanded. Now, the slow freeze picture tells you the opposite. It says the temperature in the past was lower, so the temperature has increased as time goes on, and the universe has not expanded, but it has shrinked. So that seems completely different, but it's the same physics. And it's just a different picture. And you could have other pictures, for example, one picture where the geometry does not change, where space is static. What is important in these other pictures, both the slow freeze or static universe, is that the particle masses changes. Actually, the particle masses in these pictures grow as time grows. And that is, of course, something that is quite familiar to today's particle physics. We know, for example, the masses of the electron depends on the field or the Higgs field. And so you need another field, I often call it the cosmon, that changes in time and that the masses are proportional to this field. So if the field increases, the masses increase. And for increasing masses, you can have these different pictures of the universe.
How can this idea be made consistent with observations that the universe is expanding from a hot, dense state? You know, we've got the redshift of the galaxies that we see. How does this picture fit into those observations?
What we really observe is are dimensionless ratios, let's say distances multiplied with some mass. This is dimensionless. So if the masses of particles change, you can get a very different picture. For example, in this picture of the slow freeze, the masses of particles increase with time. That means they have been smaller in the past. Now, the frequency of light emitted is proportional to the electron mass. So if the electron mass was smaller in the past, light was emitted at more reddish frequencies. And that gives you the redshift if you observe them. It's even simpler than an expansion of space. It's simply because the masses have been different. The frequencies of light when it has been emitted was different from today's frequencies.
So let's give another example. So the cosmic microwave background, we see that it's about, 3 Kelvin, 2.7 Kelvin, something like that. And the belief is that it was, thousands of Kelvin at the time of last scattering. How do you see the CMB? Like, how should we interpret what's going on in your proposal?
Well, it's a little bit a similar story. The only thing that you really can measure is the ratio of temperature over particle masses. That appears, for example, in the Boltzmann law or things like that. It's always temperature over some mass. It's always a dimensionless quantity. Now, you see, what has changed is the ratio of temperature over mass. That has decreased. That was much higher in the past than it's now. That's why we had the physics of a hot plasma in the past in both pictures. But instead of decreasing temperature, you can also have increasing mass. It makes the same. In both cases, the ratio decreases. The ratio temperature over mass decreases. So it's just different pictures with different, let's say, units of temperature in a certain sense, but they describe the same physics. It's similar to geometry, that for which you have different pictures. You have different pictures for all sorts of other things once your particles are allowed to change with mass.
So is there an analogy, actually, I was thinking, with like a shrinking ruler, maybe? Is that analogous?
It's a little bit a shrinking ruler, but the ruler is, of course, a physical ruler. You see, you need for this picture, you need some field, in this case, a scalar field, that still changes its value today. Because if you want to define a new metric and new masses, you have, for example, to multiply the metric with a function of the scalar field. So if the scalar field is constant, there is only one metric, and there is not a choice of different descriptions. But if you have a field that still changes today, you can get these very different descriptions of one and the same reality.
All right. So we'll come on in a minute to what these scalar fields are and talk about that, how that might relate to dark energy and inflation and things like that. But let's just bracket that for the moment. Tell me, what's the motivation for this model? Why not just stick with a conventional picture of cosmology? What's wrong with that?
There's a priori nothing wrong with it. But inside, once you have it, you have to pursue it. And once you have realized that there are different pictures, it can have a lot of implications. For example, it will have a lot of implications on our view on the beginning of the universe, on the Big Bang singularity. There it has very profound implications. If it's only for late cosmology, you could say, well, this is a fancy new way of saying it, but we could just always work in this so-called Einstein frame where you have the Big Bang. Because all these different frames, I have perhaps not yet said it, they are actually mathematically equivalent. You can get from one frame to another frame by a so-called field transformation, just redefining your fields.
Right. So let's talk about the Big Bang then. What puzzle can you solve that you couldn't? So let's talk. You mentioned the singularity, and obviously this is a real problem. It looks like the curvature is going to infinity. Time stops. All our equations blow up. Is that something you're saying you can avoid in this model?
Yes, I think this is one of the important things, is that actually the most common models of the beginning of the universe, so-called inflation models, they look in the Einstein frame as being singular. But then you go to another frame, and in this case you have a scalar field, which is the so-called inflaton. You go to another frame, and in this other frame, nothing dramatic happens. The universe can simply be static, for example. There is a frame where this happens. So then you start asking yourself, well, what's the physics of it? Can I distinguish it? Because you find that if you change the metric field, you change geometry, you also change your time units. And now you have to think more deeply on how to measure any physical time. And any physical time is actually measured if you consider some process with oscillations. And this is perhaps a good way of explaining the difference between a physical time and, let's say, proper time that is usually used. A physical time is the oscillations. We have, for example, the oscillations of photons. And if you have the standard Big Bang picture and you go backwards, they oscillate faster and faster. They make duck, 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 faster and faster. And of course, if this process is very fast, even though you have infinitely many ticks of your clock, it looks as if time was finite.
Right.
But then you go to a different frame, and then the ticks go regularly. Tuck, 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 tuck. All goes very slowly. Nothing goes with a dramatically accelerated pace. And in both frames, there's a map from one tick to another. So in both frames, it ticks an infinite number of times. So in that sense, physical time goes really to minus infinity. Only one frame is regular. In this case, the frame where the ticks are equal distance. And another frame has a so-called field singularity. The field singularity is a little bit like a coordinate singularity. When you look at a map of Antarctica, sometimes you have the South Pole being a whole line. Of course, it's just a point. You have a better map and nothing bad happens. No singularity happens. Here, we are not speaking about coordinate singularities, but we are speaking about singularities in field space. So there is, if you want, a bad map where the Big Bang looks very singular, but then there are good maps where nothing dramatic happens and where you see the physics much easier.
So I'm wondering, is there an analogy with the black hole singularity? So in the 1960s, it was believed that there was actually a singularity at the event horizon. And then it was shown, oh, no, this is just a bad choice of coordinates. It's not real. And are you saying the same is true of the Big Bang singularity?
There is, of course, the singularity at the center of the black hole.
Right.
And that's a bit more complicated because what you can use for a Big Bang singularity in order to find a better field choices are so-called conformal transformations. But the conformal transformations, they would not remove the black hole singularity at the center. But then there are so-called disformal transformations. And that seems well possible. And I've actually written a paper about that with some collaborators, that actually in certain frames, the singularity at the center of the black hole can also be a pure field singularity, not a real physical singularity.
Oh, interesting.
Still an interesting subject of this.
Because Roger Penrose, one of the authors of the singularity theorem, the Penrose Hakwing theorems, he suggested you can remove the Big Bang singularity with a change into this conformal picture, where basically we get the scales are the same. But he doesn't think the black hole singularity can be resolved. So you're saying maybe both can? Yeah,
you can go to more general class of transformations of the metric field, so-called disformal transformations. And there it is possible.
Right. So now you've worked on the quantum gravity theory of asymptotically safe gravity. And is there any relation between your model and this theory?
You see, there's no direct relation, but there's an indirect one. Because as I was already saying, the different pictures like slow freeze or Big Bang are just different pictures of the same reality. But what you need in order to have this slow freeze picture is a scalar field that still changes in time. And there quantum gravity plays actually a big role, because in quantum gravity, you typically need such a scalar field. And then you can make quantum gravity computations. What is the potential of this field? And you find that actually it does describe both inflation in early times and the dynamical dark energy in late times. So in that sense, there's a connection that you predict a model with a time varying scalar field. And that's the basis for these different pictures.
Right. So the key thing is this new field. And we should say a scalar field is a field that's described by just one number, right?
Yes, right. It's very simple. We know the electric field that has three numbers. It's a vector. Or we have the magnetic field, again, another three numbers. And then when you do rotations, then of course the direction of an electric field changes. Now a scalar field has just one number. And it does not change if you rotate your world. So that's why it is called scalar. It comes actually from scale symmetry. That is where it has been introduced a century ago. And now it's back actually for these questions of scale symmetry. But scalar fields are much more general. For example, mesons, pion is a scalar field, or the Higgs boson is a scalar field, and the inflaton is a scalar field. And
that's the field that is thought to drive inflation.
That's the field that is thought to drive inflation. And actually, quantum gravity computations, things I did recently, show you that the same field not only drives inflation early, but it also drives dynamical dark energy late. It's the same field responsible for inflation and for dynamical dark energy.
Right, so we've got these big mysteries, what is causing the universe to accelerate in its expansion, and then what drove inflation if inflation happened. And what you're saying then is that your model predicts that there's one field that explains both. Is that correct?
Exactly. That's this quantum gravity computation that predicts it. And it can even solve the standard cosmological constant problem, because in this computation, what comes out is that in the infinite future, the cosmological, in quotation mark, constants will go to zero. The cosmological constant is just a scalar potential. And this potential is really predicted to vanish, to go to zero when the field goes to infinity. And the cosmologies of this type are really of the type that the field is going to infinity in the infinite future.
So the conventional view is that what's driving the accelerated expansion of the universe is a cosmological constant. But I presume then, listening to what you just told me, is that you're saying it's not a constant. It's actually changing over time, and it's presumably getting weaker.
Yes, that's exactly what happens. The cosmological constant in a modern quantum field theory context is just the value of a scalar potential. Right. So if there's a minimum at a certain location and the field is sitting in this minimum, then the value doesn't change. And then you get a cosmological constant. But if there is no minimum at a finite value of the field, if the potential is always positive for finite values of the field and vanishes only when the field is infinity, then of course the potential is field dependent. And then actually there is no minimum where the field would settle. It will grow and grow and grow as cosmology go on. And finally the potential will get smaller and smaller and smaller. And that's how the cosmological constant problem is solved. And that's also why we can explain that dark energy is so small as compared to the Planck mass.
Right. So in fact, I should say that there have been hints observationally that dark energy is getting weaker over time. So DESI, for example, I hosted them announcing results that have the suggestion that dark energy is getting weaker over time. And they have told me that they will have new results that we'll see if this is real or not. So I guess your model will look pretty good if we do find that it's weakening.
In a sense, I'm waiting for that. I'm not sure that this is already really established. But in a sense, these new quantum gravity computations, they confirm what I was saying back in 87 when I proposed quintessence. It was exactly this type of scenario. And then for a long time, people...
Oh, hang on, Christoff, because not everyone will know what quintessence is. So this is this idea of dark energy changing.
It's this idea that dark energy is given by a scalar field and that it's not constant today. The scalar field changes today. So that's a very, very large class, of course, of models. And I came to it actually by thinking already at the time about quantum scale symmetry, which is very important for this asymptotic safety things. But at the time, it was just a guess. But already, for many, many years, people told me then, come on, Christoff, it's a cosmological constant. And I was never believing. I was just saying, wait until the systematics get better and better. We had even a big research project with Heidelberg, Bonn and Munich, where one of the central questions was if dark energy is static or if it's dynamical. That's well back. And by now, I think the chances are pretty good that it turns out that dark energy is dynamical. Because only in this way you can explain why it's so small.
Right.
If it's a cosmological constant, then you have to explain a small parameter or small parameter ratio. Then you have to explain what is the ratio between the cosmological constant divided by the force power of the Planck mass. And that has to be 10 to the power minus 120. But if the scalar field changes and the potential gets smaller and smaller, you just have to wait long enough, and then it's small enough.
Right. So does your calculations show how much it would be changing, or is this a sort of, no, it just will be changing, but we can't tell you the rate?
No, a given calculation can compute how much it is changing today. That's, I think, a very new development in quantum gravity computations, as in this asymptotic safety scenario, that you can really compute the form of this potential for the scalar field. Before, we used just to write down a potential, arbitrary one, just one that would suit us, and there have been thousands of models with different potentials. And my big aim is to compute this potential. And I think that's really a new development that for a given setting, fields and quantum scale symmetry conservation or preservation, you can compute it. Also, for example, for certain models where there is no quantum scale symmetry violation in the neutrino sector, you find dynamical dark energy, but a time evolution that is not compatible with observation. Right. And in other models, you can have a time evolution that may be compatible with observation. So that becomes a really fascinating period because not only, it's some general arguing, but you can really come to the point right now where you can compute certain quantities relevant for cosmology from a quantum gravity scenario.
Right. So it's been argued that the value of the cosmological constant is delicately fine-tuned in two senses. One is that it's unnatural, and the other is that it's fine-tuned for life, in that if it was slightly different, life couldn't exist, because if it was too big, the universe would expand too rapidly, everything would be torn apart. If it was too big and small, it would be pushed together. Too big and negative, I should say. So how does I guess what you're saying is it's not a surprising value at all, because in your picture it looks like it's exactly what we should expect. Is that right?
Well, that's where the different models come into play. For example, the simplest type of models, you would get so-called scaling solutions where the dark energy density is just proportional to the dark matter density. These are actually not viable, but they would explain already why the cosmological constant goes to zero when the field changes. Now, the interesting thing is that the neutrino sector in the standard model is special. It's special in the sense that it reacts to physics beyond the standard model. The so-called non-renormalizable interactions that are responsible for the neutrino masses. And as a result, there can be scale symmetry violation in the sector, and the neutrino masses, even in the Einstein frame, can depend on time. And then you find interesting cosmologies where the present dark energy density is actually more or less proportional to the neutrino mass, which is not so bad, because neutrino masses are 10 to the power minus 2 electron volts or something like that. Dark energy density is 10 to the power minus 3 electron volts to the force power. So actually numbers match. And this gives very interesting cosmologies where you link really neutrino properties to the dark energy properties.
Right. And what about other constants of nature? It's been claimed there's, I don't know, a dozen, maybe more, that they're all delicately fine-tuned for life. If they were slightly different, life couldn't exist. Do you have anything? Does this idea have anything to say about that?
Well, you see, this is the so-called anthropic principle. And for me, the anthropic principle depends always on what you know at a given time. For example, there are thousands of quantities in nuclear physics, and many of them have to be the value that they have in order to permit at least our life as we observe it. But as a result, now that we understand where nuclear physics comes from, it's just a few quark masses and the so-called confinement scale in QCD that settles all these thousands of parameters. So the question is, if we have parameters that we do not understand, they could, of course, be of an anthropic nature in the sense that they have to be because we exist so. But it's much better if we can explain them. And the big hope of, for example, quantum gravity as an asymptotic safety scenario is to explain these quantities. And there has been already a first very good explanation. I mean, with Misha Shaposhnikov, we predicted the Higgs boson mass 10 years before it was found. And 126 GeV, we were saying, plus a few GeV. That was a quantum gravity argument. And that has been much substantiated by now. So I still say this prediction is a valid prediction.
Right.
And with a little luck, we will be able to predict more quantities. How many? I don't know.
Well, we'll look forward to that. It's very exciting. So let's go back to cosmology and the early universe. So the most popular scenario is the inflationary scenario, where the universe is expanded at this exponential rate. How does the slow freeze scenario relate to the inflationary scenario?
You see, these quantum gravity computations, as I was already telling you, they predict you a scalar field that is both responsible for inflation and for dynamical dark energy. So inflation is really coming out of this type of computation. Now, once you have this inflaton field that changes, then you have to look a little bit more closer on what is really the physical content of the inflationary scenario. Is it really singular or not? And that's where it comes on that you have the different pictures, and where you can then find pictures of choices of fields where you see that actually when you go back, everything is regular. You can go in physical time, in the time that is ticking. You can go infinitely many ticks back. The universe still exists. It has started actually from a very, very boring state where essentially there was no entropy. There was just a few fields, the metric field and the scalar field with non-zero values, and then small fluctuations around it. I call it sometimes the great emptiness. Perhaps it's even better as a name as the slow freeze, because slow freeze is a bit particular. There is this feature that there was essentially nothing, and things, went on forever to the past and have never been dramatic. Only at some moment you go away from this very, very boring solution. You start producing entropy and so on, and then the Big Bang starts.
Let me ask you about that then. What was the trigger then? If it was this boring universe, nothing much happening, why didn't it just stay that way?
Well, because there's a small instability. And this instability, it concerns precisely the particle masses. The particle masses, when you go to the infinite past, in this picture, they go actually to zero. So in the infinite past, everything was relativistic. Everything was like light. But you find that if you have a tiny, tiny particle masses, tiny, tiny values of the field, because the particle masses are zero, because this scalar field is zero. If you have tiny values, it will start growing. At the beginning, it grows very, very slowly. That's the early phases of inflation. And at some moment, this effect is big enough, and the growth rate is big enough such that it ends this extremely slow motion, and then you start producing entropy and so on, and starting what is the usual Big Bang.
Right. So is this similar to what's called the emergent universe, where we trace inflation back and then we enter this static phase?
In a certain sense, similar to it, except that I'm saying that just the standard models of inflation are of this emergent type.
Right.
You do not have to go to very complicated constructions. You have just to look properly on what happens in an inflationary universe, what happens with the physical quantities, and not with frame-dependent quantities.
Right. Now, there has been some criticism of the emergent universe by people like Vilenkin and Matani, Geary and Cahias. Does that apply to your model? Do you have anything to say about those?
These criticisms are typically concerning quantum effects, and they come from a computation, that was pretty appropriate at the beginning, but it's no longer. And in this computation, you had first a type of so-called semi-classical solution, and then you added quantum effects to it. And then you never knew really what you were doing. I think in the modern view, you first include all quantum effects in order to compute the so-called quantum effective action. And then you solve the field equations that you derive from this quantum effective action, because these are actually the exact field equations. And then you can look at instabilities. And then you find, for example, that for the standard inflationary models, there is an instability, exactly the one corresponding to these growing masses in an appropriate frame, but it's a very mild instability. And nothing happens, there is no dramatic transition to some other vacuum or something like that. It's pretty boring, as I was saying. Yeah?
Right. So is it right? So this, I should explain, when we say semi-classical, we're not using a real quantum theory of gravity. They're sort of taking ideas from gravity, from quantum mechanics,
and mixing them somehow together,
Yeah.
Somehow classical solution, and then you say, I put on top of it, I put some quantum effects.
Right. But you're saying, let's do a quantum gravity calculation.
Together from the beginning. Compute already, the quantum effective action and the potential for it. And let's say the curvature scalar and higher order curvature terms and so on. You have to compute all that. And once you have it, you have just an exact statement that the field equations derived from this effective action are exact field equations. There are no more other quantum effects to be added to it. And that's a much more coherent picture.
Right. So have you compared this slow freeze picture with the standard lambda CDM model? Is there observations that can distinguish them?
Well, you see, the slow freeze picture requires that dark energy is dynamical, or that the field changes with time. So that's the real test. The real test is dark energy evolving. It will be not evolving very fast. It looks not very far from a cosmological constant, but it changes in time. Can one find out that this is true? Then lambda CDM is dead and dynamical dark energy is alive. But of course, and then you can have the different pictures.
You've claimed this model can be eternal into the past, but there are, theorems like Penrose Hakwing, Guth and Vilenkin that sort of imply that's not correct. You couldn't extend things back eternally into the past. Mm-hmm. How do you get around these theorems?
Well, these arguments are mainly based on what is called geodesic incompleteness. Geodesic sounds complicated, but let's say, in short, you could say, is time stops when you want to go back. You cannot go further backwards. So that's, of course, a bit a layman explanation. But then, if you look closer, you see that the notion of geodesics depends on the metric you are using. This is obviously because, the geodesics are given by geometry. And if the geometry depends on your field choice, the geodesics depend on your field choice. So you have to generalize this concept to a version that is independent of the choice of fields, that really reflects the physics. So I did quite a long work with Valery Rubakov on this question. And so it was clear we had to generalize the notion of geodesics. And what comes out is actually that the best way of qualifying things is just looking at physical time. And that's the real criterion. Does the clocks, the physical clocks that are present in our universe, do they tick an infinite number of times or not? If they are not ticking an infinite number of frames, then there's typically a true singularity, because then you can't go further back. If they tick an infinite number of frames, it's just up to you to find choices of fields where the singularity is not present anymore. And that is possible.
Right. So what about the puzzle of the low entropy state? I mean, this is something Roger Penrose has sort of made a big deal about, that, it seems to be incredibly low entropy at the Big Bang, and we wouldn't expect that. That's somehow surprising. And there's also this argument about thermodynamics that says, the past couldn't be infinite, because if it was, we'd be in a sort of maximal entropy state with no usable energy. What do you have to say about these?
Well, there are several things to be said about. The first thing is to say that, well, if you go to this standard inflationary picture and you look at it in the normal, let's say, in a regular frame where everything goes slow, then you start from this very, very boring state where you have only some expectation values of fields and then some fluctuations, small fluctuations. And then the entropy is essentially zero. And then it grows when the particle masses grow and you come to this instability, and then you trigger the entropy production at what is called the heating after inflation. Having said that, I should also add that entropy is actually not such a universal and robust concept. There are very many definitions of entropy. It's not just state counting. You have to specify which states are included in the counting, which not. That goes by coarse graining and so on. Is this a quantity also that is relatively well defined only for equilibrium processes, whereas cosmology obviously is not in equilibrium. So it's a useful concept. You have to be careful how to use it, however, which type of entropy you are using. And you should not overdo it in basing, your fundamental statements on entropy, because actually, once you have a given quantum effective action and you solve the field equations, there is no more to that. You can give it an entropy interpretation, which is a useful one. But, when you have your solutions of the field equations, you are done. That's the same for black holes. You do not have to have a state counting interpretation of black holes in order to understand them. You just solve them, numerical simulations for colliding black holes. You get all the physics out of it. It's just correlation functions that you can measure. And so I repeat, entropy is useful, but I'm very reluctant when people start, basing judgment of if a universe can work or not on entropy. And also, of course, the argument that entropy has to be, that the universe has to settle to some thermodynamic state. This is just not true. Because
why not? Like, it seems.
Why not? Because look out at our universe. Do you see that things go to thermal equilibrium? Things started almost in thermal equilibrium, and then structures have grown. So they are not at all going to the direction of local thermal equilibrium. And why not? Because you have gravity. You have an instability, gravitational attraction, and in presence of instabilities, the thermodynamic arguments do not work anymore. So you just see it when you look out at the universe. It started almost in thermal equilibrium and moves away from it.
Right, but isn't the claim that we can get deviations from equilibrium, but that's, whilst there are stars burning their fuel, and eventually we have to go back to thermal equilibrium. Isn't that the argument?
Perhaps not. Who knows the future, I would say. Yeah, of course, at some moment you would say the protons decay. And then you may go back to a new type of thermal equilibrium, but even that is not sure. You see, at the same time, you also discard the particles from each other by fast expansion. If you take the Big Bang, if you take now the Einstein frame, in the presence of instabilities, it's not so easy to make a clear statement on what will happen. I wouldn't make it. I would say there could be new types of structures evolving. We have even not guessed.
Right. So there's been a claim that there's not only the second law might imply a singularity or a beginning of time or something like that, but there's this thing called the generalized second law, and that implies a quantum singularity. So Aaron Wall has suggested that. Have you looked at his paper? Do you have any thoughts on that?
A little look, and it's again, of this type where you add in a certain sense quantum so-called quantum fluctuations to a semi-classical world. And I don't think this is what should be done with today's understanding. With today's understanding, you really have to look at the field equations of your quantum effective action. They tell you everything. There's nothing in addition. That's the important statement. And if they are stable or have only mild instabilities, fine.
So is the claim again that was semi-classical,
yes,
and not done in proper quantum gravity? When you do it in proper quantum gravity,
yes,
you get a different answer.
Yes. And you can run into a lot of contradictions by gluing in this way classical equations and quantum effects. I'm not criticizing, for example, Alex Vilenkin is a good friend of mine, or, there are many people, and I think it was really the thing to do at the time. But in my view, knowledge has advanced, and by now you really should go to this pretty strict rule: compute the quantum effective action, stick with it. Right. And that gives you the answer to what is predicted.
Okay, so last question then. You started the idea of quintessence, back in the 80s, I guess. And this slow freeze, I think, goes back to 2014. Have there been any new developments that you think we should be keeping our eye open that might change the picture at all?
Well, the fact that there exists different pictures for the same physics, that's mainly educational work in a certain sense, because in our head it's so deeply anchored that we have only one choice of fields, that the community has to get used to get a wider view, to see the different aspects and to see which singularities can be field singularities. So there's still some work to be done, definitely. For example, for the black hole singularity in the interior and things like that. But I think the main message that you can have different field choices, for me, that is settled. I've written in another context, actually in the context of quantum gravity, recently a paper on field redefinitions. And it comes out again that this is really true. You can use different fields. Not surprising. After all, you have differential equations and you can use different fields different variables in order to solve them. It's not so surprising. But I think this is, for me, just a matter of fact. And then, of course, in this, let's say, in the propagation of these ideas, you can still clarify certain questions. For example, the work on physical time I did with Valery Rubakov recently has, for me, still clarified quite a lot of things. So I'm not saying that everything is settled, but the basic things that you can just have different choices of fields, different geometries. Geometry loses its absolute meaning. It becomes relative again. I think that is settled for me. Now, where there is, of course, a lot of work to be done is the quantum gravity computations for, let's say, the dynamics of the scalar field. That's what you really want to predict, and that is what you really can then measure in cosmology. So, in a sense, there is a big difference between just saying there is dynamical dark energy. Dynamical dark energy you need, otherwise there is no slow freeze picture if you want. Otherwise all pictures are the same. Huh?
Right. Well, we will.
The difference is compute really what is the type of dynamical dark energy, and that is just at the beginning for me.
Right. Well, we will keep our eye on dark energy because next month, I believe, the Dark Energy Spectrographic Instrument DESI will be announcing new results, and who knows what we will find. Maybe we will see some hint of dark energy changing over time. And but in the meantime, thank you so much, Christoff. It's been absolutely fascinating. If you liked this material, please give us a like on YouTube. And if you have any thoughts on the model, please put them in the comments. And thank you very much, Christoff.
Okay, Phil. Was very nice to chat with you again. We had already a chat on asymptotic safety. So who knows, in the future we may chat again.
Yes, that would be great. That would be great. That would be great.